Find the limit if it exists. And here we have the limit as x approaches infinity of the rational function 1 minus x squared all over x cubed minus x plus 1. Now, we know we have our handy-dandy trick that says we can divide the numerator and denominator by the highest power of x in the denominator. In this case, that is x cubed. So let's do that. I'm going to write equals, I'm going to make it a little lower. I can't actually write clearly up here because there's a little recording bar. That's a little look behind the scenes. But anyways, when we do that division, this is going to become, when we divide everything by x cubed, 1 over x cubed minus x squared over x cubed is the same as 1 over x. And then in the denominator, we've got 1 minus 1 over x squared plus 1 over x cubed. And then we know the limit of a quotient is the quotient of the limits, so we can split the limit into the top and bottom. But then the limits of differences and sums become the sums of the limits, sums and differences of the limits. So let's just do this all in one step. I think we've got the hang of it at this point. We've got the limit as x approaches infinity of 1 over x cubed minus the limit as x approaches infinity of 1 over x all over the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 1 over x squared plus the limit as x approaches infinity of 1 over x cubed. That is a cubed, not a squared there. And if we look at these, all of them are 0 except for one of them, right? The limit of a constant is that constant itself, so that is 1. But all of these are 1 over x to a whole number. We know that the limit of that as x approaches infinity is 0. This is going to be 0 minus 0, all over 1 minus 0 plus 0. In the end, that is 0 over 1, and 0 divided by 1 is 0. So the limit of this function as x approaches infinity is just 0. That's because the denominator is growing at a much faster rate than the numerator. So this is going to give us fractional values that are getting closer and closer to 0 as x grows.